Okay. I think we did this one here. Yes. Because this is the one we ended on. Yep. Yeah, no, I realized when I ran the copies off the first time. So for those of you who got the ones I printed off today, you're not going to have the same exact note sheets that everybody else has. There's the one that says number 3. There's just one of them. Where everybody else has 3, I meant to erase the other 2 so that y'all would have enough space for all of them. So we finished this one up yesterday, and we'll do this one here today. And all of these here are really revolving around the equation y equals a times b to the x. Now they give us 2 points. They gave us these 2 points here, and these 2 points lie on the graph of whatever this exponential is. So what we can say for this first one, 216, when the value of y is 16, a times b, x is 2. Or whenever x is 2, y is 16. So for whatever values of a and b, 16 is equal to a times b squared. Then we also have when y is 2, a times b to the 5th. So the value of y is 2 when x is 5, or we can say when the value of x is 5, the value of y is 2. These 2 points lie on the graph of this exponential equation. And what we want to do is we want to find it. We want to find out what it is. Now, when we did these yesterday, the first thing that we did was we solved for the value of a. And not to get a specific value, but we tried to solve one of these equations so that a was by itself. Now, the one that I always pick is I pick whichever one has a value of b that is smaller. Always go after that one. Yeah, so we would look at the one that has 16 equals ab squared, because b squared is less than b to the 5th. So what we do to solve for this here is we would divide both sides of this equation by b squared. Because b squared divided by b squared will simplify to 1, leaving us with a is equal to 16 divided by b squared. Any questions on any of this here so far? Well, now that we have this solved for a, and we know that both of these a values are going to be the same because they're describing the same equation, we can plug it in to the other equation, which gives us that 2 is equal to 16 over b squared times b to the 5th. And as we looked at these yesterday, really the b squared and b to the 5th, those will simplify each other out. Because when we multiply by a fraction, when we multiply a number by a fraction, that number on the outside is being multiplied with the numerator. It's going to go on top. Bless you. So really, I'll go on and write this out. Bless you. If we multiply this together, we'll get 16b to the 5th over b squared. And 2 of these here will cancel out with 2 of the ones on top, leaving us with 16b to the 3rd. 16b to the 3rd. Any questions on any of this here? Any questions on anything we've done so far? Now, you didn't have to write out this middle step here, because if we know that b to the 5th is going to be over b squared, we can go on and simplify that out there. Now, we still need to solve for the value of b. So we can do what? Divide both sides by 16. and we'll have b to the third is equal to 1/8. Yes, then we would want to cubed root both sides. Now, the cubed root of b to the third is just going to be b. Now, when we talked about radicals, because it's been a few weeks, when we have a fraction inside the radical, we can really break it up and see and take the cubed root of 1 and the cubed root of 8. Well, what is the cubed root of 1? 1. Really, the nth root of 1, no matter what the root we're taking, is always going to be 1. Now, we also need to take the cubed root of 8. Is there a number that multiplied by itself 3 times is 8? 2. Because 2 times 2 is 4, times 2 is 8. So the cubed root of 8 is 2, which means the cubed root of 1/8 is 1/2. Any questions on how we found the value of b? Well, we still need to find the value of a. This here is the value of b. Now to find the value of a, we come back up here and plug in 1/2 for b. So we get a is equal to 16 divided by 1/2 squared. And at this point here, you can plug this into the calculator. But if we decided to do this by hand, 1/2 squared, well, 1/2 times 1/2 is 1/4. Numerator times numerator, denominator times denominator. Or really, we're squaring the numerator and denominator. And 1 squared is 1, 2 squared is 4. But really, we're dividing 16 by 1/4. And to divide fractions, we have to change it from division 2 and to flip the second one. Which tells us a is equal to 64. Any questions on how we found a and b? So again, our equation is y is equal to a times b to the x. And this here would be our equation. Now that's really all it asks us to find. But looking at this here, would this exponential be considered exponential growth or exponential decay? Almost. It's going to be decay because our value of b is between 0 and 1. If the value of b is between 0 and 1, it's considered decay. If it's greater than 1, then it's considered growth. And another kind of way that we can look at it, as x increased from 2 to 5, the values of y decreased from 16 to 2. They got smaller. Any questions on this here? Okay. What we're going to look at is this here. This here is what a lot of school districts or politicians are going to call real world problems. Essentially, it involves some type of real world, quote unquote, situation or setup. But most of the time it's been manipulated so it works nicely. It's essentially a math problem that we would do, but they wrapped a scenario around it, more or less. A source sells trampolines. The table shows the number of numbers y of trampolines sold during the Xth year that the store has been open. Write a function that models the data. Do you think the model can be used to predict the number of trampolines sold in the 15 years? So we have this here. And as we look at it, it is increasing because we do have the table here and the graph. And as we see, it is increasing up. Now, this is closer to a real world, quote unquote, as some would say, a real world situation, or at least as close as we can get. Because we can check to see the rate, 16 over 12, 25 over 26, 25 over 16. And if we simplify these here, well, 16 over 12 would reduce to 4/3. 25 over 16 won't reduce. 36 over 25, well, these don't have a common real ratio to them, but it probably is going to be considered exponential. Now, there's several ways that we can go about doing this. And we can use the process we just had and pick two numbers. So I could pick numbers 112 and 436 and go about finding A and B. And that's, again, that's exactly what the textbook would say, and I would agree that's what we could do. But as we just saw, is there really a common ratio or rate that this is increasing? No, but it is most likely going to be considered exponential. So what we're going to do is, instead of doing this by hand, why don't we use the resources that are available at our disposal? So what do you think we could use to help us solve this? The graphing calculator. Let me put both of these down. The graphing calculator. Now, there's something we want to turn on first. So what I want you to do is, if you have your calculator, make sure it's turned on, and go second 0, second catalog. And you should get something like this here. We've gone over this once before, and this here is every possible feature that this calculator has is set up in here. Now, what we want to get to is diagnostics on. Now, one of the ways we can do, and I can see some of y'all are doing it, is hitting the down arrow, yes? Have y'all noticed that it has a full alphabet in there in green? And if you notice up next to the battery symbol, it says A, or up in the top corner. Now we have this A kind of lit up. What that tells us is that alpha, anything in green, is accessible. So what I can do is say, okay, A, B, C, D, is I can click it, and it jumps me all the way down to D. So it helps you kind of jump through the list, especially if you're trying to find anything with S. I can click the one that says S, and it'll jump me all the way down there. But at this point, we will have to scroll down some, and I go too far. So do you guys see diagnostics on? Yes? Hit enter once you get there. And it should say diagnostics on, hit enter, and it says done. We kind of got that? So this here is going to be helpful, and I'll point it out what this did and what this turned on. Now what we want to do next is go stat, edit. Stat, there should be a button that says STAT. Nope, just stat, and then edit. So you click the stat button and then really hit enter. And you should get something like this here. If you do have numbers filled in, we're going to eventually need to clear them out. And we'll clear them out as we go. So we got all good? Now, on your note sheet, we do have the data already on the table. And what I'm going to do is I'm going to fill in the x values, 3, 4, 5, 6, 7. I put all the x values into L1, into the first list. If you have anything beyond that, what you can do is you can cursor down to below it So, yep. So I just type right over the top of it. And then if you ever get more data below it, if you hit the delete each time, it'll just delete that column out. I'll put these back in, say anything below 6, and it's not for this here. But if I had information beyond that, if I hit delete, it'll pull the numbers up. I don't have to keep going down. But we do need 6 and 7. I'm going to go over. So those are our x values. Well, guess what we're putting in L2? The y values. So we'll say 12, 16, 25, 36, 50, 67, 96. So we have our table here. Yes? Okay. Now, I'm going to show you this here so you kind of see what it does. You don't have to follow along with this here. I'm going to hit y equals. Come up here, and what I've done is I've turned on plot 1. For some of y'all, when we've been graphing, how you've had issues and that your screen kind of looked like that there, plot 1, that one up top was highlighted in some way. I've turned that on. Now, I have to mess with this a little bit. 0 to 10, let's go by 0.5. And then y min is 0 to 100. And I'm going to go by 10. Graph. Well, that's the graph we have on the table, yes? So that stat plot, what I can do with it is I can plot individual points on a graph. So we have this here. Okay. Second quit. Hit stat again. So you can go second quit to get back to the home screen. And we want to hit stat again. So we want to get back. So you can go ahead and hit stat. Yep. Nope. Just hit stat. Because we want this screen. So everybody right here. Now we're not going to edit this time. I want to go over to calculate. And what this will do, so we're in calculate. Now there's two types of functions that this could be. One of them is that it could be too far. Is this that it could be a quadratic regression, a quadratic type of line. So let's do it. So go down to 5, have it highlighted, hit enter. We have this, so those of you who do have your calculator have this screen up. What this is telling us is L1, so the x values we put into L1, it's telling the calculator all these values in L1 are the x values for this function. Y list, L2, so all the values in Y2 or L2 are the y values for this function. So it's saying these are the points. Now we don't normally concern ourselves with frequency, but let's store this. There is a way we can store it. Now what I'm going to do is I'm going to hit alpha, and you know you've hit alpha because it has a little A printed in there for alpha. And what we're going to hit is trace. So you should get this little window popped up here. Y'all see that? Now we're going to hit enter this time. And you should have Y1 written there next to store. Yes? What this is telling it is that, okay, one, it's a quadratic equation. It's going to find out what the equation is for a, b, and c for our ax squared plus bx plus c. And then we said stored in Y1. So where we graph where it says Y1, it'll put the equation that it finds in Y1. Okay? Go down to the very bottom at calculate, tell it to calculate it. And we get this here, yes? Now, r squared, that r squared, y'all see that at the very bottom? That is what we turned on when we turned on diagnostics. Okay? Now this r squared number, and it sometimes gives us r, is telling us how close the numbers are to the equation. So if we looked at the distance between the equation and our point and calculated that up, this is telling us how close it is. The closer to 1 or -1, the closer it is to 1 or -1, the better the data is. The better this equation represents the data that we have. Does that make sense? The closer to 0 that it is, the worse the equation is. That means the distance from the line is huge. We don't want that because it's calculating the distance above and below the line. So the closer to 1 this is, the better off we are. The farther away from 1 it is, the worse off the data is. So I'm going to hit graph because I do already have this set up. You don't have to hit graph. So we have this here. Yes? Okay. Now, we've been looking at exponentials, yes? Okay, let's go back to stat. Over to calculate like we just did. And this time we want to go farther. Exponential regression. Well, this is for our exponential equations. Has everybody found this? EXP? Once you find it, go on and hit enter. Exponential regression. So L1, L2, don't care about frequency. I'm going to go alpha, trace, and this time I'm going to scroll down to Y2 because Y1 already has the quadratic equation, so I'm going to put it in Y2 to give us the exponential. We good with this here so far? Okay. Now the first one, the quadratic, was really close because I believe we got 0.996 going on out, yes? But this one here is what? 0.998. So what that tells me is that this exponential regression is actually a closer approximation to the actual equation. This gives us a better representation of the data, an equation that better represents the data than the quadratic did. This is closer. Well, the blue line was our quadratic, and the red line is our exponential. And as we see here, the red line does follow those points just a little bit closer. So questions on this here? So I'm going to hit a few buttons real quick. And what I'm really going back to is this here. Okay. Hopefully I didn't hit it too many times. Here is our equation. Now, if it's asking us what the equation is, we can use this to figure it out. And really what we would do, so the equation is what? A times B to the x, yes? Is equal to, well, A, I'll take it 3 spots, 8.457. It gave me the value of A. The value of B is 1.419 to the x. And that's the equation for the exponential. Now, the downside to this here is this is actually a better answer than what we could have found by hand. Because if we're trying to find it by hand, we can only pick 2 of these points at a time. This here, this calculator is taking in consideration all 7 points. Where with our calculations and what we did on the previous ones, we can only do 2 at a time. This did all 7. This is a closer value for this here. Because I have messed with this already, and if we pick the first and second numbers, we'll get a value for A and B. If we pick the first and third, we would get a different value, slightly different, not a whole lot, different value for A and B. first and fourth. Each one would give us a slightly, I'm talking about hundredths, if not thousandths, of a decimal place difference for each one. And they'll adjust accordingly. So when we get to more real-world data, as you can see here, these decimals are not nice. We don't get nice whole numbers, do we? And that's what the real big issue with most, if we take real-world, actual real-world data that we're trying to model, it's very rare that we'll get nice whole numbers, okay? There's a reason that, especially for large calculations, they do most bomb testing now all on computers. There's not actual, they put them together and actually blow them up. They don't do that anymore, but they need supercomputers, I mean huge computers to do these calculations. There was a guy doing research at JBU got grants through NASA to do, let's see here, he was for physics, dealing with physics and these massive calculations, and he would run most of them over the summer because they were able to work it out that the programs that he was using would outsource the data and calculations to every campus or every computer on JBU's campus to turn it into one big supercomputer because it couldn't do the calculations otherwise. So a lot of it, especially real-world data, it doesn't work well in nice numbers. We have these big numbers, these not nice round numbers like these here. Now, would it make sense, this here, after say 15 years or 20 years, would we expect this kind of sales of trampolines? Yes, no? What do y'all think? Huh? Because their sales are increasing exponentially, yes? Would you expect to see someone making sales exponentially continuously forever? Well, no. It doesn't work out well because, I mean, we can put it to anything. So makeup sales. Are we always going to have an increase in makeup products? No. Because it'll increase, it'll decrease, it'll go up, it'll go down depending on products and sales because it could be everything's working out fine. Well, now there's a shortage in springs. Well, I can't keep increasing because I can't make more. Because product demand, we cannot have this continual exponential growth. Now, we can look at this here with the exponential. And what's really cool and kind of nice is I'm going to turn off this here. And in graph, this here with this function, something we can do is I can go second calculate, and I can calculate a value. So let's say, because it asks for 15 years when x is 15. Yeah. Go to zoom 0. And that should give me a big enough window. Now I can go second calculate value 15. Okay, fine. I'm going to make you give me a value big enough. 20. Second calculate value. Because if it's not considered in the window, it won't figure it out. It's temperamental at times. Enter. So after 15 years, he is supposed to have sold 1,607 trampolines. That's a little excessive, isn't it? Second trace value. Boop. Now let's say he sold, average person worked 60 years. So he sold trampolines his whole life for 60 years. 11051. So 11051 e to the what? 10? 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. So over the course of his life, after selling trampolines for 60 years, he should have sold 1,105,000. I missed a number. That should not be that. That should be 11,051,000,000 trampolines. There's no way over the course of 60 years you're going to sell 11 billion trampolines. That's a little outrageous, would y'all say? Yeah. If they did, they just named themselves Lawsuit Emporium. But most of these functions are well and work well for a certain amount of time over a certain period. After that, we have to change it and make predictions and changes. Because they can help us with making predictions over a short period, but over a long period, they kind of fall apart. But that's all we're going to do today.